Good morning, everybody. Hope you're doing good. We are almost at the end of the semester. Maybe we could even finish before next week. Let's see what happens. Okay? Is it better or it is worse if we finish it sooner? Okay. So, any questions? What we were talking last time was the combinational components. We talked about parity. After multiplexer, we talked about parity, comparator, and then we talked about an application maximum failure. Yeah, remember? Any questions? So we had two questions for getting your reflections. Let's see, what did you write? The first one. It says that search for another error detection mechanism other than parity, because the parity we have discussed in the course. So it was only one bit added, and it could only detect error if there is only one error. If there are more than one bit, it cannot detect, and it cannot fix also. So let's see, what did you write? Jin Yuan. There? No. Anna. No. Morgan. Yeah, Morgan. Very good. So Morgan picked up CRC. Very good. Cyclic redundancy check, CRC. I guess you have heard about CRC before. If you are going to buy a RAM for your computer, you could see that it mentions which CRC they are implementing in the RAM. CRC is an error detection method that is used in conjunction with parity. It entails expressing the data as a polynomial and dividing it with a generating polynomial. So every bit could be considered a coefficient in a polynomial. The division result is the CRC code. So if you get a polynomial and then divide it by a specific polynomial, then you get something. The remainder would be the CRC code, the division result, which is attached to the original data, and it contains more bits. How many bits do you know? I don't remember myself. I guess there are different CRC 8, CRC 16. So it depends on the polynomial that we would like to get. And you add a number of bits, not just one bit, as it was with parity, to the data. Again, we use redundancy to be able to detect the problem, the errors. If the remainder is 0, okay. The received message is split by the same generating polynomial. If the remainder is 0, there were no mistakes. Otherwise, errors might have occur. CRC can identify more sort of mistakes, not just one error, including multiple bit errors and burst errors. It does not, however, rectify faults, and is primarily used to detect flaws in communication protocols. Usually we do have it in our communication protocols like IEEE 802 and these things. Very good, Morgan. So this CRC is a known error detection mechanism. Let's go to the next question, which we had discussed in the class also. We had the competition for that. The comparator which has been presented in class was for unsigned numbers. Discuss if it works for signed numbers or not. Consider two positive numbers, two negative numbers, and one positive and one negative numbers to see if it works or not. So Anna has not arrived yet. Yeah, Morgan, we talked with him. Ivan, Ivan is there? Ivan. Very good, Ivan. Okay. So, Ivan, comparator works with the sign numbers. So, very small. Let's see what did you write. For 2 positive and 2 negative numbers, the magnitude of the numbers can be compared directly. Very good, Ivan. Even in the first place, we are thinking that no, because it should not work for negative numbers, but it works. The same thing that we had, starting from the left digit, going one by one inside to see if it is bigger or smaller or equal. For 1 positive and 1 negative number, the number with the negative sign bit is considered smaller. Very good, Ivan. Perfect. Any questions? So let's continue, okay? We were here. We talked about this. Let's move on. The next component that we are going to discuss is adder. Adder is a very good component in combinational circuits. And then if we want to add 2 numbers, A plus B, then we need an adder. Again, as we always that we talked about it before, if you have, let's say, 2 4-bit numbers, okay, for example, A, B, 2 4-bit numbers. Let's say A is 1 0 1 0, B is 0 1 0 0, for example, whatever it is. Then you want to calculate the sum. 0 plus 0 becomes 0. Then, sorry, there is no carry. 1 plus 0 is 1. 1 plus 0 is 1. 1 plus 0 is 1. So that would be the result. If you, let me write 1 here, so I get a carry also. 1 plus 1 is 0 with a carry here. 1 plus 0 plus 1 is 0 with a carry here. 1 plus 1 plus 0 is 0 with a carry here, and there is a carry here. So the result would be 1 0 0 0 0. If you look at this, using the systematic way that we talked before the midterm, it always works. You can write the truth table for that. We have 8 inputs, and we have 1, 2, 3, 4, 5 outputs. So we could have a truth table of 2 to the 8 is 256. 256 rows, which the inputs would be A0, A0, A1, A2, A3, and B0, B1, B2, B3. So there are 8 inputs starting from 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1 up to 255. And then calculate for each of these combination what would be the result for S0, S1, S2, and S3 plus carry out. That's something that we could do. But we talked about this, that it's not a good way to do so. But we are going to use some kind of RTL design, some kind of functional design, some kind of component-based design. So what do we do? So again, an example, let me do this example again. This is 1, 2, 3, 8 bits. 8-bit numbers, 1 plus 1 is 0, and then we have a 1 carried over. 1 plus 0 is 1. No carry. 1 plus 1 is 0 with carry. 1 plus 0 plus 1 is 0 with 1 carry. 1 plus 1 plus 0 is 0 with carry. 1 plus 1 plus 1 is 1 with carry. 1 plus 0 plus 0 is 1. And 1 plus 0 is 1. So that would be the result, and there is no carry out. So this is correct. This is not correct. With carry out. Okay? So that's how we do that. This is exactly the same as you do in decimal. Everybody knows how to do the decimal. To adding 5, 3, 7, 9 plus 6, 2, 8, 3. 9 plus 3 is 12. We have carry. 1 plus 7, 8 plus 8 is 16. 1 plus 3, 4 plus 2 is 6. 5 plus 6 is 11. 1 with carry is 11. So that would be the result. Yeah. Yes.
So if the result is over than 8.
It goes up. Let's do that. For example, you have 3, 5, 6 plus 2, 6, 5. Okay? Octal, base 8. 6 plus 5 is 11, but which is 11 is 1, 3. 11 is 1, 3 in octal. 1, 3, yes. 1, 3. So it is 3 with 1 coming up. 6 plus 5, 11 is base 10. But in octal we have 0, 1, 2, 3, 4, 5, 6, 7, 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, 2, 0, 2, 1, 2, yes. Is that right? Yeah, it's the base 8. We start from 0 going up to 7, then 1, 0 going up to 1, 7, then 2, 0 going up to 2, 7, and so on. Okay? So 6 plus 5 is 1, 3. So 1 coming out. 1 plus 5, 6. Plus 6 is 12 in decimal. In octal, it would be 4, 1, 4, 12. 1 plus 3 is 4, plus 2 is 6. So the result would be 6, 4, 3. Okay? So in any base, you can do that. Even in the binary is the simplest way because we have only two numbers, 0 and 1. In decimal, we have 10 digits. In octal, we have 8 digits. So this, you see how did we do that? If we would like to design a circuit for that, instead of going for the truth table, here even it is 16 inputs, which would be 2 to the 16. Wow, it is a 64K truth table, which we never can simplify that. But we do something like that. Look here carefully. I guess I can erase everything here. So if you look here, for example, 1 plus 1 is 0 and 1 coming higher. For each slice, look at each slice. For each slice, we do the same thing, very similar thing. And in this slide, how many inputs do we have? 3. One, AI, BI, and the CI coming from the previous stage. So we have 3 inputs. And how many outputs do we have? 1 plus carry. We have 1 as a sum and 1 as a carry going out for the next stage. So we have something with 3 inputs and 2 outputs. So it's very easy. Let's do the truth table, let's do the Carnot map and simplify the design. That would be easy. That would be manageable. 3 inputs, 2 outputs. So this is how we do that. So we have a component. We call it, you see, we call it later full adder component, full adder element. It accepts a carry from the previous stage. Then it has 2 digits for this bit position, and that there would be a result of sum and a carry going for the next stage, CI plus 1. So this is AI, this is BI, this is CI coming from the previous stage, and this would be SI, the result, and this is carry I plus 1. The next carry goes for the next digit. Okay, so easy. A component with 3 inputs, 2 outputs. Let's draw the truth table. So the truth table would be something like that. AI, BI, CI are the inputs. So there are 3 inputs. So we have 8 combinations, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, so on. And we have 2 outputs, SI, and carry for the next stage, which I call it carry out. A carry in, a carry out. Okay? So easy. So this is the truth table. If you look at the Carnot maps, this is the Carnot map for S, and this is the Carnot map for CO, carry out. Very simple. For S, if you look at the Carnot map for S, there are here Carnot maps for that, and these are the locations that we have odd number of ones in our inputs because we are adding them together. If we have 1, 1, then the result would be 1. If we have 2, 1, then the result would be 0 with a carry. If we have 3 ones, then again the result would be 1 with a carry. So if there is odd number of ones, then it is 1. If it is even number of ones, then S would be 0. Yes? Follow? Everybody? Agree? So how could you build a circuit for odd parity? Right? Last lecture we had it. How did we implement parity generator? What was the element? It's a very useful element for parity. No. Yeah? XOR. Very good, Eric. Perfect. So XOR is a very useful component. It gets inputs, and based on the odd number of inputs, it generates either 1 or 0. So this is easy. We just use it an XOR. This one, carry out, if you look at the ones, we have 1 when we have more than 2 ones in our input, either 2 1 or 3 ones. So it is some kind of majority calculation. If we have 2 ones or 3 ones, we can use a very simple AND to do that. So let's do this. Before that, let me show you the symbol. This is the symbol for full adder. As you could see, it is an 8-bit full adder. 8-bit. We have an input of 8-bit for A. Did we talk about this, that we put something on the cross it with a number 8? Did I talk about it before? It is a bus with 8 wires. So it is 8-bit number. This is 8-bit number. It is A0, A1, A2, A3, A4, A5, A6, A7. So when I put a cross here with a number, it means that this is a bus of 8-bit wires. Again, the second number B is also 8 bits, and we have a carry in. So we use a carry in here because later you could see that we would like to cascade them. But for the first addition, we don't need this carry. It is 0 because we don't have anything before that. So it is 0. And then the result would be 8-bit plus a carry out. So this is the full adder, 8-bit full adder. So what would be the circuit? So as I told you, this is odd parity calculation, and it is very simple. With 2 XORs, we can do that. 2 XORs will do the job. If you have 1, 1, or 3 ones, SI would be 1. If you have 0 ones, no ones, or 2 ones, the SI would be 0. So this is first one. And the second one was majority calculation, which I used 3 AND gate. So if both of them are 1, we have 1. If AIBI is 1, so 1. If AICI is 1 here, then we get 1. If BICI is 1, so we get 1. So either one of these ANDs, which shows 2 of them are 1, generates 1 at the output, which is the carry out. Simple. So we built full adder, just 1 bit full adder. And now we are using this 1 bit full adder to make, for example, 8-bit full adder. Very simple. I still could even a little bit simplify. I removed one and used the result from this XOR, the result from XOR, this XOR, and use it. So I made a simpler circuit. They are the same thing. So if you look at this circuit, it generates SI and CO, and it accepts the inputs are AI, BI, CI. Okay. If you look at this part doesn't get CI. Sometimes, for example, for the first stage, we don't need CI. So we call this half adder, not full adder. Full adder accepts also CI, but half adder is just AI and BI, generating SI and CO. So this is half adder, and this is full adder. Everything is there. Okay? Now that we built 1-bit full adder, let's use it and build a longer full adder. So this is the first one. We have 2 numbers. Let's say we have 4-bit numbers. The 4-bit numbers is A0, B0, A0, A1. I wish PowerPoint put some kind of short key for eraser, but it doesn't. It has a short key for pen. Control P goes to pen. But for eraser, I have to come here, and then maybe there is something that I don't know. If you know, let me know. Go there for eraser. Okay, so we have 2 numbers, A0, A1, A2, A3, a 4-bit number, and also another number, B0, B1, B2, B3, for another number. Okay, if you have questions, ask me. Okay. So we use full adder, the first full adder, for the first slice, A0 and B0. So A0 and B0 come to our full adder, and because it is the first slice, we don't have any carry coming from the previous stage. We put 0 for our carry in, which is called C0 here. C0 is 0, A0, B0 is fed into the full adder, so we get S0 and C1 coming out of this full adder. Now we are going to the next stage. As you have seen, we get the carry from the previous stage and add it to A1 and B1. So this is exactly what we do here. So we get this carry from the previous stage, and we connect A1 and B1 to the inputs of this full adder. Now we get the result of S1 and carry 2. Now we connect the carry 2 to the next stage. So carry 2 is connected to the next stage. Carry 2 plus A3 plus B3 is becoming S2. Carry 2 plus A2 plus P2 outputs S2 with carry 3. And now the last stage, carry 3 plus A3 B3 produces S3 and the carry out. Here carry out is carry 3, the last bit is 3. So carry 3 is carry out. Okay? We built, yes?
What is the ripple?
What is? Oh, okay. I am just now going to explain. So you see carry coming from the previous stage. So there is a delay for and before that is also like that. Whenever we had a cascade circuit, I was telling you that the delay is accumulating and the delay is becoming more. Here is the same thing because these are our 3 inputs, our 3 first input, and it takes time to generate S0 and C1. S0 is okay because it goes out. That's it. But C1 going to the next stage, and until C1 becomes ready, we cannot calculate S1. So S1 should wait for C1. Okay? So the delay is accumulating. Again, here it generates C2. Again, the delay of this plus the delay of the previous stage are accumulated, and C2 will be generated with a delay. Now C3 will be generated. So the carry is rippling among these things. So we call this ripple carry adder. Carry is rippling among these things. And this kind of adder, which is very simple in design, as you saw, but it is slow. We could have faster adders which somehow try to find the carry ahead of time without waiting for the previous stage. We call, for example, them carry look ahead adder. This is another kind of adder which we don't discuss it in our course. But there are different structures for adder which would be faster. But this ripple carry adder is very simple, and it is slow. You see the carry going through the stages, and it takes time to generate the output. Now that we have talked about adder, let's talk a little about incrementer. Incrementer is also a very good component. Actually, incrementer is a special kind of counter. A special kind of adder. When we add what to a number? What do we add to get incrementer? 1. If you add 1 to something, you incremented it. So it is a specific adder, but just adding 1 to it. Since the incrementer has only 1 operand, we just increment A. So there is not like add, which we added A plus B, 2 operands. Incrementer just has 1 operand, A, so we could use half adder to make this. Let's see the half adder. So in the half adder, you remember, half adder had A and B inputs without carry coming as the first stage and generating carry. So if we use this half adder, and instead of A0 we put 1, number 1 here, so we are adding 1 to B, and then it can goes to the next stage. So the carry out from here goes again for A1, and this is added to B1. Again, the carry from here goes to A2, and that is added to B2, and so on. So here you see this S0, S1, S2, S3, they are 1 plus B, incrementing B. Whatever B is, S0, S1, S2, S3 is the increment of B, is B plus 1. And we might have also a carry out coming out. Okay? Oh, that is also a good circuit. That's a use of half adders, because you might ask, why do we have half adder? We can use it for incrementer. Now we talked about adder. What about subtractor? So we find out how to calculate A plus B, whatever bits they have, 4 bits, 8 bits, 16 bits, whatever they have. What about A minus B? What would be your suggestion? So the first suggestion, let me do the first suggestion, you do the second suggestion. The first suggestion is exactly like the add, we can have a subtractor. Let's put, first I do in decimal, then I go to binary. For example, 1,268 minus 3,459. In decimal, how could we do that? We go from 8, so it is less than that, so we get 1 from the previous one, so it becomes 5. Sometimes you add 1 to the bottom or decrement from the top, so whatever you do. So we get is from that, so it becomes 9. So we have 5, from 5 is 0. 4 from 2, again we get it from here. 4 from 12 is 8. And 3 from 0, again we get something from the here. So we have a borrow from here. 3 out of 10 is 7. So it is 7809, actually minus. No, what did I tell you? 1, 2, 3 out of 10, 7. And we have some kind of, what is this? What is this number? Do you know what is this number? What? 1,268 minus 3,459. How come it becomes 7,800? Huh? What? Complement. How do we do that? This borrow means that something is wrong. It couldn't be there. It couldn't be there. So what does it mean? Let me see. What does it mean? So we borrowed 1 from here. So it means that this number minus, because we borrowed, minus 10,000 is the result. So actually that number is the negative of the result, the complement of the result. You can do that. So if you do that, you see that the result would be something around 2,000, minus 2,000 something. Okay, I made a bad example, but that's good, because you saw what would this borrow means, and it means that number should be complemented, should be negated. Okay, so now let's do it in binary, but this time I would make a simpler example. Let's say the first bit binary number is 1011. The second one is 0010, for example. If you look at that number, it is 8 plus 3. It is 11 in decimal, and this is 2 in decimal. The result we expect to be 9. So let's see it. So 0 from 1 is 1. 1 from 1 is 0. So it was very easy. Let's make it a little bit harder. So let me do it 0 here. So it becomes 9. 9 minus 2. So again, okay. So I made 0 here. Now let's do it. 0 from 1 is 1. 1 from 0 is we should get something. So we should get, for example, it became 10, and we can add 1 here or decrement from the top. 1 from 10 is 1. 1 from 10 is 1. Now we have 1 here. 1 from 0, it doesn't work. So again, we get something from here, and we make it 10. 1 from 10 is 1. And then we have 1 from 1 is 0. So the result is 0, 1, 1, 1, which is 7. 9 minus 2 is 7. So it is okay. It was a simple. If the number was smaller than the second number, that would be harder, difficult. So this is my first suggestion, but I didn't want to do this. What is your suggestion? How do subtract? Complement and then add. Yeah, we had talked about 2's complement before. So instead of a minus b, we do a plus minus b. And what is minus b? What is 2's complement of b? We complement every bit and then add 1. So that would be the thing. We get b bar plus 1, which would be minus b, 2's complement of b, and then add it to a. Let's see how it works. The same example. I had 1, 0, 0, 1 minus 0, 0, 1, 0, 9 minus 2. So I make 2's complement of 2. The 2's complement of 2, if we go to the fast method, I start from the right. You remember, I start from the right. We go to the first one, we keep it, and then negate every other bit. So this is minus 2. So we add this minus 2 to 1, 0, 0, 1. 1 plus 0 becomes 1. 0 plus 1 becomes 1. 0 plus 1 becomes 1. 1 plus 1 becomes 0, and there is a carry. Here you see we got this good result, 7. We got result with a carry. When you are doing subtraction using addition, this carry means borrow not. If it is 1, it means that there was no borrow. So everything was okay. You see, there should be no borrow. 9 minus 2 is 7, no borrow. But if it is 0, this time, if it is 0, it means that we had borrow for our subtraction. So here, in addition, when there is a carry, means it is not complete in, for example, 4 bits. We needed another bit. If there is 1 in subtraction, then it means that everything was okay. But if it is 0, then it means that no, it was not okay. We needed another bit. We are now we are going gradually to signed operation, not just unsigned. You see, there are 2 signed numbers. We did a 2's complement and then added to them. Sorry. So if we had the adder, before going further, we had this adder before. How could we use this for subtraction? Easy. You get b inverted and also plus 1. So we put 1 for carry in. Before we put 0 for carry in. And now we have add. Look at this circuit. This is a minus b. Okay? Yeah? A minus b. B is inverted. We had a 1 added to it, and it is added to a also. So the result would be subtraction. So this circuit is now doing the subtraction of a minus b. How could we use a circuit for doing both of them? Because we are using adder for both of them. So somehow we need a configuration, a control signal which controls the circuit. Either it is add or it is subtract. So we use a control signal. A control signal like this. Did I talk about this notation before? When you have something like that, add bar slash sub, it means what? It means that this control signal, if it is 0, is this one. It adds. If it is 1, it subtracts. When we write some kind of this, with this notation, when you look at this, you find out if it is 0, it means add, because it is active low for add. When it is 0, it adds. If it is 1, it is active high for sub, so it subtracts. So let's build a circuit doing that. Okay, our circuit was an adder. If we have 0 for this control signal, so I put 0 for this signal. So what I would expect is that A and B coming to the adder untouched, unchanged, and also 0 goes to carry in. So you look at here, 0 comes here, 0 is here, 0, 0, 0. Again, we have the very good gate of XOR. When you XOR 0 with something, we get the same thing. 0 with anything would be that thing. So B is coming here, B3, B2, B1, B0 coming here. So we are adding A to B with carry in 0. So this is an adder circuit. Now let's assume that the control signal is 1. So let's assume it is 1. When it is 1, this one goes here, one input of XOR, and also goes here. The control signal goes there. So you see, what happens now? We have XOR with 1. What it does, XOR with 1, it inverts, it complements. So we have B3 bar here, B2 bar here, B1 bar, B0 bar here, and also we have 1 here, and this is exactly the circuit of subtractor. B0 is negated, 1 is added to it, so A0 plus B bar plus 1 is A minus B. So you see, with adding just a simple control signal and adding 4 XORs, we could build a universal circuit doing both addition and subtraction. Just putting the control either 0 or 1. If it is 0, it adds. If it is 1, it subtracts. Okay? Is it a good circuit? Do you like it? Add or subtract. Now that we have talked about add or subtracted, why not making it more complete, more complete, more complex? We built an ALU. ALU is arithmetic logic unit. We need something to do addition, subtraction, and, or, and other things. We call it ALU. So, for example, I want an ALU to do these things. When it operates on the operands, on the inputs, it also generates some flags. For example, our adder and subtractor was generating a carry out. A carry out is a flag. So it shows if we are adding and it is 0, then it means that the result is good. If it is 1, it shows that the result is not good. Something we need something to do for that. So there is a flag. Also, we could have some kind of flag. We will talk about it later. Let's say I want to build an ALU doing these things. A plus B, we talked about this. A minus B, where is A minus B? I didn't put A minus B. Here. No. I wish I've put a minus b here also. Anyhow, eight functions I've put. A plus p, a times 2, maximum a and b, a and b, a or b, 2's complement of a, so just one operand. The same a, so it does nothing, just outputs a, and the invert of a. So let's say we want to build something like that. How do we do that? Yeah. Yeah, multiplexer is a very good solution for everything. Multiplexer. So we have something, we just play with the inputs of the circuit with multiplexer, then we have everything. So we could use multiplexer to build that. I am not going to show you the full circuit. Maybe it's a good question for your exam, to build an ALU with multiplexer and everything. Okay? So that's it for RTL combinational components. We have covered decoder, multiplexer, mux-based design, parity circuit, comparator, adder, subtractor, incrementer, ALU. Okay? And now, after that, we were going to memory elements, which we had already covered. Now we are going to the 7th topic, actually the last topic, which would be sequential components, RTL sequential components. I again remind you, we started from the logic, then we show you how to simplify the design, then we talked about component-based design. We talked that there are sequential and combinational parts everywhere, and then we talked about combinational components, and then we went to sequential. I will give you the overview right now. So I stop it here.